chapter. Okay. We've nearly finished the chapter, and in the tutorials yesterday, we looked at some of these exercises. So this is exercises 3.2 on page 22. We looked at some of these problems in the tutorials yesterday, on Monday. And so I'd just like to look at a few other of these examples here. So there are more applications of, well, the ones in the tutorial were mainly applications of the fundamental theorem of arithmetic using the prime factorizations of integers to prove things. And I'd like to focus on these two exercises here, questions 10 and 11. These are kind of about that, or more just applications of divisibility again. Okay, so we're going to look at, let's look at question 10 for a start. So what's this question asking us to do? This is prove that if 2 to the n minus 1 is prime, then so is n. Okay, so this is a nice result. These numbers are kind of special. They're all one less than a power of 2. So these special numbers, if they are prime, it turns out that the exponent n has to be a prime number as well. Okay? It doesn't mean that if n is a prime, then 2 to the n minus 1 is definitely a prime. But in order for 2 to the n minus 1 to have any chance of being a prime, this result is saying the exponent has to be a prime as well. So this is related to, or this concerns, so-called Mersenne primes. So Mersenne primes are prime numbers, primes of the form 2 to the p minus 1, where p is prime. These are typically the largest known primes that we know about. Okay, so numbers of this form, 2 to the p minus 1, are maybe quicker for the computer to check the primality of. So you're aware of this idea that through computer search, we've been able to find larger and larger primes. So currently, there'll be some world record at the moment for the largest prime known to us humans, and it's a prime number of this form, 2 to the p minus 1, where p, the exponent p itself, is some large prime number. Okay, and you can get involved in this if you do a search on Google for GIMP, or maybe not for GIMP, but for what it stands for. Be a bit careful. It's the Great Internet Mersenne, it's actually GIMPs actually, the Great Internet Mersenne Prime Search. I don't know what the laughter is about, but if you search this, the Great Internet Mersenne Prime Search, that's a distributed computer project. So you can download a program, install it on your PC or your computer. What it does, if you leave your computer on and you're not using your computer, what the program does is, while the computer is just sitting there not being used, it starts up this GIMPs program. And what it does is it keeps searching. It coordinates with all the other instances of it running around the world, and it takes a batch of large numbers and it starts searching them and testing them to see if they're prime or not. And if you're incredibly lucky, maybe your computer will be the one that discovers the next largest known prime to humankind, and you'll get your name mentioned in a paper somewhere because you or your computer will have discovered the largest known prime. It's pretty bad. I should have looked it up before I came here to to see what the exponent is for the currently largest known one. Does anybody, have you just looked it up there? Good.
I've already looked at it before. That is 57,885,161.
So, yeah. So that itself is a prime number, but 57 million is tiny. You know, that's in the scale of these things, that's no big deal. But this number, 2 to the 57 million and whatever minus 1, 17 million and a half digits long itself, but that is a prime number. Okay, and I think that was found by some, I think it was maybe some mathematics lecturer or something. Curtis Cooper. Yeah, good. This is good. You're a good teaching assistant. So that's the largest known one, and so he just had this program running on his computer or computers, and it happened upon that this is the largest known prime to man at the moment, to humankind at the moment. Okay, so you know, you can get involved in that if you want to. You might wear your computer X. It'll keep your computer working away furiously all the time if you leave it on. Anyway, but let's have a go proving this exercise. So this related fact. If 2 to the n minus 1 is prime, then so is n. So let's try and prove this. So it's a proof of question 10, not the fact that this is prime. So we want to show that 2 to the n minus 1 is prime, but that implies that n is prime. And this is, you know, there's some general mathematical tips to pick up from this kind of problem, or some general mathematical lessons to learn about approaching proofs and how to get a handle on proofs. Because at the moment, you might think, well, where do we begin with this? Because you're asked to prove this implication, that if that is prime, then n has to be prime. If you try and prove it directly, so if you assume this and then try and deduce this, it's a little bit tricky, because saying that a number is prime, it's kind of like a negative statement. You're saying something is prime, you're saying it can't be factorized, it can't be broken down. And the conclusion you're trying to prove is that n is prime. So you're trying to prove a negative conclusion. You're trying to prove that there's no way of factorizing n. And it's, if you tackle it directly like that, it's a bit frustrating because you've nothing to get a handle on. If you assume, so you say, assume 2 to the n minus 1 is prime. Well, that doesn't give you anything straight away. It gives you a negative thing. It says, well, you can't factorize 2 to the n minus 1 down. So there's nothing to get a handle on. There's nothing to get a grip of to try and work the proof, okay? There's nothing to get a handle on here if you just think of proving the implication directly. So what is, you know, or from your, is there an equivalent statement to this? So this is an implication. The thing on the left implies the thing on the right. What's another equivalent way of saying an implication? Or what is there a different statement that's equivalent to this one? You would have met this in first year logic. If you've got an implication A implies B, there's a closely related statement which is equivalent to it. Begins with C. It's kind of longish logical term. It's the contrapositive. The contrapositive of an implication. So if A implies the contrapositive of A implies B is not B implies not A. And that's equivalent to the implication A implies B. So rather than tackle this, which looks a bit there's nothing to get a hold of there, you can think of its contrapositive. So we'll try and prove, instead, we'll try and prove the contrapositive of this. Now, what's the contrapositive? So it's going to be implication going in the other direction, and it's going to say n is not prime implies 2 to the n minus 1 is not prime. So in other words, that says n is composite implies that 2 to the n minus 1 is composite. They're the negations. Saying something is prime, the negation of it is to say that it's not prime, it's a composite number. Now this is much more approachable. When you think about proving this statement directly, you can immediately get started, can't you? Because if you assume n is composite, that immediately gives you ammunition. What's the ammunition it gives you? This is a positive statement now. It says n is a composite number. Maybe not 2, but it has some factor. It has some genuine factors. So it's a positive statement. Out there somewhere, there are some genuine factors of n. So we can call upon them because we know that they exist. So we can write n, say, as s times t for some integers s and t, and these are genuine factors. So we're not writing n as 1 times n again. So they're both strictly bigger than 1. They're 2 genuine factors. I guess we should be talking about an integer n bigger than 1. Yeah, well, that's maybe not important. Okay. Well, this is much better because now you've got 2 new objects here, and maybe you can do some work with them. Okay, that's good. Now think about the conclusion you're trying to reach. The conclusion we're trying to reach is that 2 to the n minus 1 is composite. So what's the statement 1 up from that? Has factors, so it's something times something. Now that's good. This gives you something to aim for. We want to fill these gaps with genuine factors of 2 to the n minus 1. So we want to place an integer here and an integer here, and we want them both to be strictly bigger than 1. Yeah. So to be genuine factors of 2 to the n minus 1. And we've just introduced s and t, so the insinuation is that s and t are going to feature down here. Something to do with s and t are going to feature down here. Yeah. So that's good. That gives us a really clear beginning and an end. So we want to get 2 to the n minus 1. So, well, there it is. There's 2 to the n minus 1. And you see, we've given ourselves, even without starting to really puzzle it out, just by following the kind of basic principles of setting out the starting point, setting out the end point, it's kind of telling us what to do. Because I'm start with 2 to the n minus 1, but I've just gone to the trouble of introducing s and t. So I should immediately think of this as 2 to the power s times t minus 1. I want to get down to here. I want to factorize 2 to the n minus 1. Here I've got 2 to the n minus 1, and I've got the n bit factorized. You just want to hammer away at it. Try and rip that apart. Try and factorize it. What can you do with that? Well, you can maybe start to think about some general algebraic techniques for factorizing expressions. I mean, you're familiar with the idea that differences of squares factorize, if you've got a difference of squares, a squared minus b squared, that factorizes. If you've got a difference of cubes, that factorizes as well. A squared plus ab plus b squared. And well, these patterns continue. Difference of fourth powers also factorizes, so it'd be a cubed plus a squared b plus ab squared plus b cubed, etc. So there are these kind of standard algebraic factorizations that you can do. And they work in general. If you've got a to the m minus b to the n, you can always separate off a factor a minus b from that. And the associated thing is, well, what these terms are here is they're products a times b. Products a times b, where the orders, the sum of the indices is always one less than the power over here. You got order 2 terms here, order 2 being one less than cubes. Here you've always got order 3 terms, cubes squared times an order 1, a 1 times an order 2, and a cubes. So the general form of it is you always have, so you're going to sum over j, and the sum of the indices is always m minus 1. So you can have j here and m minus 1 minus j. And j goes from 0 up to m minus 1, is it? Yeah, m minus 1. So there's a general fact there. And we can employ that here. Because we can think of this first bit as either 2 to the s to the power t, or conversely 2 to the t to the power s. And you're subtracting 1, but you can re-express 1 as any power, can't you? 1 is equal to 1 to the s, or 1 to the t. So we can say this is, you can think of this now as, you can think of this like that. So it's a difference of powers, the same power t in both cases. And so we can at least factorize it into the product of two numbers. You may well factorize more, but what we want is just to factorize it in one step. So we can employ, sorry, did everybody get that? Okay. Yep. We can apply that and say we're going to get 2 to the s minus 1, that's my a minus b, times, well, it's going to be 2 to the s minus 1 plus 2 to the s minus 2 plus 2 to the s minus 3, all the way down to plus 2 plus 1, 2 to 0. So that is just applying this. That's just applying this factorization result where you've got a being 2 to the s, b being 1, and m being t. Yeah, so you pull out 2 to the s minus 1. Actually, the way I've written it down here, these, when you start going j equals 0 up to j equals m minus 1, you're actually starting here and you're going there and then going there. So this is the j equals 0 term, this is the j equals 1, that's the j equals 2, and so on, all the way up. Okay. So the point is, it does factorize. It does factorize like that. Oh, wait a minute. No, wait a minute. Sorry, that's not right. I haven't done it right. No. Silly Killian. It's not as simple as that. Sorry, this is 2 to the... Sorry, it's s into t minus 1. Sorry. is 2s into t minus 2. And sorry, you're counting down these, finally 2 to the s, and then plus 1. Sorry. That's what it is, yeah. But we get to factorization. So these are our two factors here. Those are our two factors. Now, the only thing we just have to check is this a genuine factorization? We just have to be careful that we haven't just rewritten this as 1 times itself. Well, that's okay, because we have this condition, because s and t were genuine factors, so they were both strictly bigger than 1. If s and t are both strictly bigger than 1, that ensures that both these brackets are strictly bigger than 1. So it is a genuine factorization. Both factors meaning these two things, both factors strictly bigger than 1, since s and t strictly bigger than 1. So what the statement proved there is that if n is a composite number, then the 2 to the n minus 1 is also a composite number. So that's the contrapositive of the result that's phrased there originally. If this kind of number, if a 2 to the n minus 1 number, if it's prime, the exponent n has to be a prime number. Okay. It's not saying that if n is prime, then definitely 2 to the n minus 1 is also prime. That's not true. You probably get a few quick counterexample. They may, I think they might all be prime for the first few, but then they fail to be. But if this kind of number is going to have a chance of being prime, then the exponent has to be prime. Okay. So we know now that two to the n minus 1 prime implies n prime. So that's related to these numbers known as Mersenne primes. So following it is quite a closely related problem, question 11. Except this doesn't deal with 1 less than a power of 2, it deals with 1 greater than a power of 2. Two to the n plus 1 is prime, implies n is a power of 2. i.e. n is equal to 2 to the m for some integer m. So the only time numbers like this can be prime is when the exponent is a power of 2. And these are known as Fermat numbers. Which are 2 to the 2 to the 0 plus 1, 2 to the 2 to the 1 plus 1, 2 to the 2 to the 2 plus 1, 2 to the 2 to the 3 plus 1. All these kind of numbers are known as Fermat numbers. That's the famous French mathematician Fermat, which Fermat's last theorem fame. And when he was investigating numbers like this, when you look at the first few of them, so you've got 3, 5, that's 2 to the 2 to the 2. That's 6, that's 17. The first few of them are actually all prime. And he made a conjecture. He conjectured they were all prime. I.e., all of the infinite list of numbers, so that 2 to the 2 to the n plus 1 is always prime. But he was wrong because the next one isn't. The next one is a composite number. 1, 2, 3, 4. 2 to the 2 to the 4. So 2 to the power 16 plus 1 isn't. So it's not true. Okay, but obviously they didn't have computers in those days, so that number was too large for him to do any direct calculation with. But eventually someone did. Euler? Legendre? Someone did find a factorization of this, I think, fairly soon. Okay, but he was onto something, though. He was onto something because in order for this kind of number, 2 to the something plus 1, in order for that to be prime, it's a requirement that the exponent is a power of 2. The implication doesn't go the other way. If the exponent is a power of 2, it doesn't imply that 2 to the n plus 1 is prime. But it is a necessary condition. It's not a sufficient condition, but it's a necessary one. But again, I think the way to do this is to do the same kind of approach, because it's a bit hard to get a grip on this directly, because it's a negative assumption you make at the start if you try and prove this directly. So it's better to go to prove the contrapositive. So the contrapositive is if n is not a power of 2, that implies that 2 to the n plus 1 is composite. Now, this kind of looks like a negative assumption that you're going to make at the start. N is not a power of 2, but it's not like a negative assumption in the way that saying something is prime. Something is prime, there's, you can't say anything more about it really in terms of factorization. But if you know n is not a power of 2, then you know it has a factor which is not 2. So we know there exists some odd factors of it. Okay. So we're going to prove this directly. So we assume n is not a power of 2. So if it's not a power of 2, I mean, maybe it has some powers of 2 in its factorization, but it must have at least, well, it has another part to its factorization. So there might be a whole load of 2's inside n, but there's at least, that's not all there is. There are some other factors. So we can write n like this, where s, which is strictly bigger than 1, is odd. Okay, that's the point. So to prove this, we assume that n is not a power of 2. And if it's not a power of 2, then we know we can always write n like this. There may not be any 2's here. So m could be 0. It may be that just n is an odd number. There mightn't be any 2's in its factorization, but maybe there are some. But there's an odd part to its factorization as well. And then I think it's just replaying the technique we used before. We're trying to get the conclusion that 2 to the n plus 1 is composite. So we want to write 2 to the n plus 1. We want to factorize it into a proper factorization. But there's our n, so you can launch right into it. 2 to the n plus 1. This is 2 to the 2 to the m by s plus 1. Still looks a bit tricky, but what do we know here? Well, we know about these factorization results, which are to do with differences of powers. Differences of powers. At the moment, this isn't looking like a difference of powers because it's a sum. It's a plus. But is it a minus? Could you arrange that there's a minus there instead? And you've got some same power of something here and here? Well, you can do that because that plus, you can think of that plus as just two minuses, minus, minus. And the fact that S is odd, I mean, it's a little bit of a trick, I guess. Yeah, put brackets around that, and you've got an S there. So you can rewrite this thing like this. It's a bit kind of jiggery pokery. It would take a little bit of puzzling to arrive at that. See, because this is minus 1 to the power S, but S is odd. So the minus 1 to the power odd is going to give you minus 1 again. You got minus minus 1, so that gives you plus 1. And here we've just taken the S outside, so it's 2 to the m to the power S. Okay. So now this is a case where we can employ this kind of factorization. So we can extract out the factor 2 to the 2 to the m minus minus 1 out of that. So we can apply this kind of factorization here. We know we can factorize this as 2 to the 2 to the m minus minus 1. Minus minus 1. And there's some other stuff here. So this will be an alternating sum of these objects over here. But let's be lazy and let's not even write it down. We can be a bit lazy. Okay. So I can factorize this. So this will be 2 to the 2 to the m plus 1. And there's this other factor here. Okay. So there's the factorization. Now, I'm being a bit lazy by not writing this down. Let's not be so lazy. It's 2 to the 2 to the m. And this is s minus 1. And then it's minus 2 to the 2 to the m, and that's s minus 2. So it's this kind of alternating sum. It goes positive, positive, negative, positive, negative, and all the way down to positive 1. Positive 1. Positive 1, positive 1. So that's the other factor. And both of these factors are strictly bigger than 1. M is bigger than or equal to 0, but even if m was 0, it's still 2 to the 2 to the 0. Well, 2 to the 0 is 1, so you've still got 2 to the 1, so you've still got 2 plus 1, 3. So you have a non-trivial factor there. And the fact that s is strictly bigger than 1 means that this number is bigger than 1 as well. Okay. So these are genuine factors. So genuine factors meaning they're both strictly bigger than 1. Genuine factors since m is bigger than or equal to 0 and s is strictly bigger than 1. Okay. So that there is the contrapositive of this interesting statement in the exercises related to these Fermat primes. Okay. So if these kind of numbers ever want to be prime, the exponent in them has to be a pure power of 2. Some number 2 to some power. Okay. So any questions about that, or any points you'd like me to clarify on that? So also something to take away from that is how sometimes switching to the contrapositive of a statement kind of gives you places to get a hold of, and it allows you to make progress more easily. Okay, so let's come back to the notes. I mean, there's still a few things that we haven't talked about at the end of that chapter 3. And I'll go through this material so we've got 2 lectures next week. So we'll finish these, we'll give a proper consideration of these next week. But we've got a few minutes. I just thought I'd, well, tell you a little bit of a story. I mean, the material here isn't really, it's more just for information. So it's about famous conjectures in number theory. So number theory has lots of these famous open problems, or famous, problems which still haven't been solved yet in them. And one of them is called the twin primes conjecture. Okay, so this was noticed quite early on, that you often find primes which are separated by 2. So things like 3 and 5, I'm going to struggle now, 5 and 7, 11 and 13, 17 and 19, okay? So you keep seeing, if you look through the list of known primes, you keep seeing every so often there occurs a pair of primes which are separated by 2. And those are called twin primes, primes that are the closest possible to each other. You can't have a prime followed immediately by a prime because one of them has to be even, yeah? 2 consecutive numbers, one of them has to be even. So apart from at the beginning where you've got the prime 2 and 3, you never have primes immediately consecutive. But when they're as near as possible, when you have a prime as near as possible, that's called a twin pair. And it's a famous conjecture that these twin primes occur infinitely often. So there's an infinite number of those twin primes. And in all the computer searches of the integers and determining all the primes, it keeps on happening that people keep seeing twin primes. So we found them out to large numbers, and it's conjectured that there's an infinite number of them. It still hasn't been proved, but there has been some, it's kind of hot off the press. There was some progress made last year in 2013. It's a Chinese-American mathematician, Yitang Zhang, and it kind of came out of nowhere. He wasn't a famous mathematician, or he wasn't a well-known number theorist. He was just working away at a small university in the States, but he announced a proof that he had proved, not that there's an infinite number of twin primes, but he had proved that there's an infinite number of primes which have a separation at most 70 million. The conjecture is that there's an infinite number of primes that have a separation of 2. There's an infinite number of prime pairs that have a separation of 2. He was able to make some progress at that and say, well, I can prove that there are an infinite number of pairs of primes which have separation at most 70 million, right? Well, at least that's a first stab at getting, at shrinking the gap down to 2, knowing that the gap is somewhere up around 70 million was some progress made in that. So this was extremely big news, because the first time anyone had ever been able to say for definite that there's an infinite number of prime pairs which have a bounded separation. But the conjecture is that the bound is 2, but he was able to show that it's no bigger than 70 million. And that immediately sparked a flurry of work. And there's a very famous American mathematician called Terence Tao, and he's taken advantage of the internet. He has initiated these kind of online collaborative mathematical research projects. So rather than just him working with a few selected mathematicians, that likes. He's opened it up completely and done these kind of public research efforts and invited everybody in to collaborate on the research project, and they coordinate it all through a website and stuff. So that's called Polymath, Polymath, and there are a number of these projects now. People have started to kind of exploit the kind of collaborative, kind of Wikipedia style, getting everybody coordinated via a central website, but free and open, so anybody can take part in the project and contribute to it. And they took the techniques started by Zhang and they improved upon them, and they were able to shrink Zhang's original bound of 70 million. They're able to shrink that down. I think the current smallest they've got it is 246. So they've proved now that there are an infinite number of pairs of primes with the separation of at most 246. The conjecture is it's 2, and there's, you know, people. I think people kind of believe it. There's a good gut feeling that this is probably true, but what they've only been able to prove so far is that they can get that bound down to 246. And it may be that they've optimized those techniques now. It may be that they won't be able to shrink that any further without coming up with some significant new ideas or not. Now, that's all some quite advanced stuff, which we won't be able to access in this course, really. But we will be able to prove, so next week I'm going to prove something for you which is kind of related to that. So we won't be able to prove that these prime pairs occur infinitely so often. But what we will be able to prove is that there are arbitrarily long runs of consecutive composite numbers. So a run of consecutive numbers is like, consecutive composite numbers is like 8, 9, 10. There's a list of 3 numbers and they're all composite, right? We'll be able to prove, and we can prove it using some very simple techniques, just using the basic idea of divisibility. So suppose you want to find a consecutive run of 1,000,000 composite numbers. We'll be able to give a recipe for where such a consecutive run of 1,000,000 composite numbers starts. So we'll be able to produce a formula that says, well, if you start at this number, the next 1,000,000 numbers, the next 1,000,000 integers are all composite numbers. So this is kind of like the reverse of the twin prime conjecture. The twin prime conjecture says that primes occur very close together, separated by 2, infinitely often. And this kind of proves something in the opposite direction, saying, well, you can find runs of integers where there's no primes as long as you like. You can find these consecutive runs stretching for as long as you like, okay? So we're going to prove this next week, and if you want to make a stab at it, it just uses basic results that we've already looked at about divisibility and the factorial construction. So if you want to start trying to puzzle this out, think about factorial numbers. That might give you a clue about how to construct a formula for where these consecutive composite runs start. Okay? Okay, well, we'll end it there for today.